Time does not exist. A radical new view of the cosmos, ****. The distinction between past, present, and future is only a stubbornly persistent illusion. Albert Einstein. For decades, the notion that the universe began with the Big Bang and has been expanding ever since has dominated cosmology. According to the prevailing lambda CDM model, the universe is approximately 13.8 billion years old, and its expansion is driven by mysterious forces like dark energy and dark matter. But a growing number of physicists and cosmologists now believe that this model may be deeply flawed, not just in its details, but at its very core. What if time, as we know it, doesn't even exist? Einstein's warning and the James Webb Telescope's revelation. Einstein hinted over a century ago that time might not be what it seems. He proposed that time and space are not separate absolute entities, but interwoven into a flexible fabric, space-time, that bends and stretches under the influence of mass and energy. In one of his most famous quotes, he observed, "Time and space are not the conditions in which we live, but modes in which we think." That philosophical insight may now be gaining empirical backing. The James Webb Space Telescope, JWST, with its unparalleled sensitivity, is offering glimpses of a universe that appears far older, more complex, and structurally organized than the lambda CDM model can explain. These findings are driving a re-evaluation of our understanding of time and reality itself. The crisis in cosmology. Cosmology is facing a crisis. Central to this crisis is the so-called Hubble tension, a significant discrepancy between the two primary ways we measure the expansion rate of the universe. One method uses the cosmic microwave background (CMB), a relic of the early universe, while the other uses type Ia supernovae in the relatively nearby cosmos. Both are precise, but they give incompatible answers. If the universe really behaves uniformly, why do these methods yield contradictory results? The standard model, lambda CDM, tries to explain this with a patchwork of assumptions, including the existence of dark energy, an invisible force accounting for roughly 70% of the universe. But dark energy, like dark matter, remains purely hypothetical. It has never been observed directly. The increasing reliance on such unproven entities is beginning to resemble scientific mythology more than empiricism. Enter the timescape model, a new cosmological paradigm. Physicist David Wiltshire and his team at the University of Canterbury in New Zealand propose an alternative, the timescape cosmology. Unlike lambda CDM, which assumes a smooth and homogeneous universe, the timescape model embraces the inhomogeneity we actually observe. Galaxies clustered into walls, filaments, and massive voids of near-empty space. The timescape model builds on Einstein's general theory of relativity, but incorporates the idea that time itself flows differently in different regions of the universe. In this framework, time passes faster in underdense areas, voids, and slower in denser regions, like galaxy clusters. What we interpret as cosmic acceleration and attribute to dark energy might simply be an illusion caused by these regional differences in the passage of time. This isn't science fiction. Wiltshire's work rigorously tests these ideas against observational data, including supernova distributions and large-scale cosmic structures. In multiple instances, timescape provides a better match with the data than the lambda CDM model, without needing to invoke dark energy at all. Time as a local, not universal, phenomenon. Imagine you're in a vast cosmic void, one of the enormous empty regions in space that span hundreds of millions of light years. Within that void, time would appear to pass more quickly than in a dense cluster of galaxies. To you, it might look as though distant galaxies are moving away at an accelerating rate. But this could be a temporal mirage, not a physical reality. If we, as some studies suggest, reside in the KBC supervoid, then our entire observational standpoint is skewed by this effect. It would mean we are misinterpreting cosmic measurements because we assume time flows uniformly everywhere. The dark energy we infer from this apparent acceleration might be no more than a projection error caused by our position in a time-warped part of the universe. A universe without age? This leads to a staggering implication. What if the universe has no age at all? In a timescape universe, the question, how old is the universe, might be meaningless. Since time flows differently depending on local conditions, the idea of a singular, universal clock becomes nonsensical. Each region of space could have its own timeline, its own now. Rather than unfolding in a linear chronological sequence, the universe might exist in a kind of eternal present, where past and future are constructs of our perception. This resonates with the philosophical view that time is not fundamental, but emergent, an illusion created by consciousness or perspective. Voids, superstructures, and the collapse of the Standard Model. The JWST has uncovered massive cosmic structures, walls, filaments, and voids, forming far earlier than lambda CDM predicted. These findings challenge the idea that structure in the universe gradually formed over billions of years from small, evenly distributed fluctuations after the Big Bang. The rapid appearance and symmetry of these voids suggest that the universe might have always looked this way, or at least, that the Big Bang model is incomplete. Voids also bend and distort light in ways that challenge standard physics. Redshift anomalies, unexpected galaxy velocities, and asymmetrical motion, like bulk flow, all hint at forces or dynamics beyond the lambda CDM framework. Timescape offers a cohesive explanation. If time itself is variable, then these distortions are to be expected. Einstein was right again. Einstein's insight into the relativity of time was not just mathematical. It was profoundly philosophical. He saw that our experience of time was dependent on context. As he famously explained, when you sit with a pretty girl for an hour, it seems like a minute. But sit on a hot stove for a minute, and it seems like an hour. That relativity may extend not just to individuals, but to entire galaxies and cosmic regions. Quantum physics, thermodynamics, and the timeless universe. Time also plays an ambiguous role in quantum mechanics. Many fundamental quantum equations, like the Schrödinger equation, don't include time as a variable. Quantum particles can exist in multiple places, and possibly times, simultaneously. This timeless quality of quantum physics aligns well with the timescape view of a universe, where time is relative and emergent, not fixed or absolute. Even in thermodynamics, where time is linked to entropy, the so-called arrow of time, the direction of time is probabilistic, not fundamental. Time, in this sense, is just a way of keeping track of increasing disorder, not a basic feature of reality. The future of cosmology. The timescape model doesn't just challenge our cosmological math. It asks us to rethink the very nature of reality. Is time a fundamental aspect of the universe, or just an artifact of our limited perception? If time is local, not universal, then the age of the cosmos, the speed of its expansion, and even its origin may be questions without meaningful answers, at least within our current scientific framework. What is certain is this: cosmology is entering a new era. As new data floods in from the James Webb Space Telescope and future observatories, models like timescape will be put to the test. The ultimate answers may not only redefine science, but our place in the universe. Until then, we must embrace the mystery. Because perhaps, as Einstein warned, we have been chasing shadows, measuring time in a universe that never needed it.